Hi everyone, I am Bhumika from BSc Honors First Year Chemistry and my roll number is 04. In this video, I am going to read the chapter The P block elements. The P block elements are placed in group 13 to 18 of the periodic table. Their valence shell electronic configuration is ns2n1p6. The properties of p block elements, like that of others, are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy, and electronegativity. The absence of d orbitals in the second period and presence of d and f orbitals in heavier elements have significant effects on the properties of elements. In addition, the presence of all three types of elements, metal, metalloids, and nonmetals, bring diversification in chemistry of these elements. Having learned the chemistry of elements of group 13 and 14 of the P block of the periodic table, you have learned chemistry of the elements of subsequent groups in this unit. Group 15 elements. The group 15 includes nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloid character. Nitrogen and phosphorus are non-metal, arsenic and antimony metalloids, and bismuth is a typical metal. Occurrence. Molecular nitrogen comprises 78% by volume of the atmosphere. In the Earth crust, it occurs as sodium nitrate, NaNO3, called chiral sulfate, and potassium nitrate. It is found in the form of proteins in plants and animals. Phosphorus occurs in minerals of apatite family, which are the main components of phosphorate rocks. Phosphorus is an essential constituent of animals and plants' matter. It is present in bones as well as living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found as sulfide minerals. The important atomic and physical properties of the group elements with their electronic configurations are given. This is the table in which atomic and physical properties of group 15 elements are shown. Trends of some atomic, physical, and chemical properties of the group are discussed. First, electronic configuration. The valence shell electronic configuration of these elements is ns2 and p3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Atomic and ionic radii. Covalent and ionic radii increase in size down the group. There is a considerable increase in covalent radius from nitrogen to phosphorus. However, as Es2 bismuth, only a small increase in covalent radius is observed. This is due to the presence of completely filled d or half filled f orbitals in heavier members. Ionization enthalpy. Ionization enthalpy decreases down the group due to the gradual increase in atomic size because of the extra stable half-filled p orbitals, electronic configuration, and smaller size. The ionization enthalpy of group 15 elements is much greater than that of group 14 elements in the corresponding periods. The order of successive ionization enthalpy are shown. Electronegativity. The electronegativity value in the general decreases down the group with the increasing atomic size. However, amongst the heavier elements, the difference is not as much as pronounced. Physical properties. All the elements of these groups are polyatomic. Dinitrogen is a diatomic gas while all others are solids. Metallic character increases down the group. Nitrogen and phosphorus are non-metals. Arsenic and antimony metalloids, and bismuth is a metal. This is due to the decrease in ionization enthalpy and increase in atomic size. The boiling points in general increase from top to bottom in the group, but the melting point increases up to arsenic and then decreases up to bismuth. Except nitrogen, all elements show allotropy. Chemical properties. Oxidation state and trends in chemical reactivity. The common oxidation state of these elements are -3, +3, and +5. The tendency to exhibit -3 oxidation state decreases down the group due to the increase in size and metallic character. In fact, last member of the group, bismuth, hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreases down the group. The well or characterized bismuth compound is BiF5. The stability of +5 oxidation state decreases and that of the +3 state increases due to the inert pair effect as we move down the group. Nitrogen exhibit +1, +2 and +4 oxidation state also when reacts with oxygen. Phosphorus also show +1 and +4 oxidation state in some oxyacids. In case of nitrogen, all oxidation state from +1 to +4 tend to disproportionate in acid solution. Similarly, in case of phosphorus, nearly all intermediate oxidation state disproportionate into +5 and -3 both in alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth becomes increasing stability with respect to disproportionation. Nitrogen is restricted to a maximum covalency of 4 since only 4 orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell which can be used for bonding and hence expand their covalence as in PF6 negative charge. Anomalous properties of nitrogen. Nitrogen differs from the rest of the members of the due to its small size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and with other elements having small size and high electronegativity. Heavier elements of this group do not form pi-pi bonds as their atomic orbitals are so large and diffuse they cannot have effective overlapping. Thus, nitrogen exists as diatomic molecule with a triple bond between two atoms. Consequently, its bond enthalpy is very high. On the contrary, phosphorus, arsenic, and antimony form single bonds as pp and A single bond A single bond As and Sb single bond Sb, while bismuth forms metallic bonds in the elemental state. However, the single N bond is weaker than the single pp bond because of the high interelectronic repulsion of the non-bonding electrons owing to the small bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects the chemistry of nitrogen is the absence of d orbitals in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form pi-pi bond as the heavier elements can. Phosphorus and arsenic can form pi-pi bond, also known as the transition metals, when their compounds like P C2H5 thrice and As C6H5 thrice act as ligands. Dinitrogen preparation. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid dinitrogen distills out first leaving behind liquid oxygen. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with the sodium nitrate NH4Cl in the presence of NaNO2, then gives nitrogen and H2O and some moles of NaCl which is in the aqueous solution. Small amounts of nitrogen oxide and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through the aqueous solution of sulfuric acid containing potassium dichromate. It can also be obtained by the thermal decomposition of ammonium dichromate. Properties. Dinitrogen is a colorless, odorless, tasteless and a non-toxic gas. Nitrogen atom have two stable isotopes. It has a very low solubility in water and low freezing and boiling point. Dinitrogen is rather inert at room temperature because of the high bond enthalpy of N triple bond N. Reactivity, however, increases rapidly with rise in temperature. As higher temperature, it directly combines with some metals to form predominantly ionic nitrides and with non-metals covalent nitrides. Ammonia. Ammonia is present in small quantities in the air and soil where it is formed by the decay of nitrogenous organic matter. On a small scale of ammonia is obtained from ammonium salt which decomposes when treated with caustic soda, and calcium hydroxide. In accordance with Le-Chatelier's principle, high pressure would favor the promotion of ammonia. The optimum conditions for the production of ammonia and are a pressure of 200 into 10 to the power 5 pascals, a temperature of approximate 700 Kelvin, and use of catalysts such as iron oxide and small amounts of K2O and Al2O3 to increase the rate of attainment of equilibrium. Phosphorus is found in many allotrope forms, the important ones being white, red, and black. White phosphorus is a translucent white waxy solid. It is poisonous, insoluble in water, but soluble in carbon disulfide and glows in dark. It dissolves in boiling point NaOH solution to an inert atmospheric, giving pH 3. White phosphorus is less stable and therefore more reactive than the other solid phases under normal conditions because of angular strain of P4 molecule, where the angles are only 60 degree. It readily catches the fire to give dense white fumes of P4O10. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin in an inert atmosphere for several days. When red phosphorus is heating under high pressure, a series of phases of black phosphorus is formed. Red phosphorus possesses iron gray luster. It is an odorless, non-poisonous, and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus and it doesn't glow in dark. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in sealed tube at 803 Kelvin. It can be sublimated in air with an opaque monoclinic or rhombohedral crystals. It does not oxidize in air. Black phosphorus beta is prepared by heating white phosphorus at 473 Kelvin under high pressure. It does not burn in air up to 673 occurrence. Oxygen is the most abundant by all of the elements on Earth. Oxygen forms about 46.6% by mass of Earth crust. Dry air contains 20.946% oxygen by volume. However, the abundance of sulfur in the Earth crust is only 0.03 to 0.1%. Combined sulfur exists primarily as sulfates such as gypsum, Epsom salt, and baryate, and sulfides such as galena, zinc blende, and copper pyrites. Traces of sulfurs occur as hydrogen sulfide in volcanoes. Organic materials such as eggs, proteins, garlic, onion, mustard, hair, and wool contain sulfur. Electronic configuration of the group 16 elements have 6 electrons in the outermost shell and have ns2 np4 general electronic configuration. Atomic size and ionic radii. Due to the increase in the number of shells, atomic and ionic radii increase from top to bottom in the group. The size of the oxygen atom is however exceptionally small. Ionization enthalpy. Ionization enthalpy decreases down the group. It is due to the increase in size. However, the elements of this group has lower ionization enthalpy values compared to those of group 15 in the corresponding periods. This is due to the fact of group 15 elements have extra stable half-filled p orbitals electronic configuration. Electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. Electronegativity. Next to fluorine, oxygen has the highest electronegativity value amongst the elements. Within the group, electronegativity decreases within an increase in atomic number. This implies that the metallic character increases from oxygen to polonium. Physical properties. Some of the physical properties of group 16 elements are given to oxygen and sulfur are non-metals. Selenium and tellurium metalloids, whereas polonium is a metal. Polonium is a radioactive and in short-lived. All these elements exhibit allotropy. The melting and boiling point increase with an increase in atomic number down the group. The large difference between the melting point and the boiling point of the oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule, whereas sulfur exists as polyatomic molecule. Chemical properties. Oxygen states and trend in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxygen state. Since the electronegativity of the oxygen is very high, it shows only negative at oxygen state as -2 except in case of OF2, where its oxidation state is +2, other elements of the group exhibit +2, +4, and +6 oxidation states. +4 and +6 are more than common. Sulfur, selenium, and tellurium usually show +4 oxidation state in their compounds with oxygen and +6 with fluorine. The stability of my +6 oxidation state decreases down the group and stability of +4 oxidation state increases. Bonding in +4 and +6 oxidation states is primarily covalent. Anomalous behavior of oxygen. The anomalous behavior of oxygen, like other atoms of p block present in the second period, is due to its small size and high electronegativity. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. The absence of d orbitals in oxygen limits its covalency to 4 and in practice rarely exists 2. On the other hand, in case of other elements in the group, the valence shell can be expanded and covalent exists 4. Dioxygen. Preparation. Dioxygen can be obtained in laboratory by the following ways. First, by heating oxygen containing salt and chlorates, nitrates, and permanganates. Second, by the thermal decomposition of the oxides of metal in the low electrochemical series and higher oxides of some metals. Third, hydrogen peroxide is readily decomposed in water and dioxygen by catalysts such as fine refined metals and manganese dioxide. On large scale, it can be prepared from water or air. Electrolysis of the water leads to release hydrogen at the cathode and oxygen at anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and fractionally distillation to give dinitrogen and dioxygen properties. Dioxygen is a colorless and a odorless gas. Its solubility in water is to extent 3.08 cm cube in 100 cm cube water at 293 Kelvin, which is sufficient for vital support of marine and aquatic life. Simple oxides. A binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with some of the elements of the periodic table to form oxide. In many cases, one element forms two or more oxides. The oxides vary widely in the nature and properties. Oxides can simple or mixed. Simple oxide can be classified on the basis of their acidic, basic, or amphoteric character. An oxide that combines with water to give acid is termed as acidic oxides. For example, SO2 combines with water to give H2SO3 and acid. As general rule, only non-metals oxides are acidic, but oxides of some metals in very high oxidation state also have acidic character. The oxides which give a base with water are known as basic oxides. For example, CaO combines with water to give Ca(OH2). Ozone. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in the atmospheric at sea level. At a height of about 20 km, it is formed from amphoteric oxygen in presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of UV rays. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, the conversion of oxygen to ozone occurs. The product is known as ozonized oxygen. Since the formulation of ozones from oxygen is an endothermic process, it is necessary due to a silent electrical discharge in its preparation to prevent its decomposition. If concentration of ozone greater than 10% are required, a battery of ozonizers can be used and pure ozone can be condensed in a vessel surrounded by liquid nitrogen. Properties. Pure ozone is a pale blue, dark blue gas and a violet black solid. Ozone has a characteristic smell and in small concentration it is harmless. However, if the concentration rises above the 100 parts per million, breathing oxygen becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in the liberation of heat and an increase in entropy. These two effects reinforce each other, resulting in large negative Gibbs free energy change for its conversion into oxygen. It is not really surprising, therefore, the high concentration of ozone can be dangerously explosive. Group 17 elements fluorine, chlorine, bromine, iodine, and astatine are the members of Group 17. These are collectively known as halogens. The halogens are highly reactive non-metallic elements like Group 1 and Group 2. The elements of group 17 show great similarity amongst themselves. That much similarity is not found in the elements of another groups of the periodic table. Also, there is a regular gradations in the physical and chemical properties. Astatine is a radioactive elements occurrence. Fluorine and chlorine are fairly abundant while the bromine and iodine less so. Fluorine is present mainly in as insoluble fluorides in small quantities are present in the soil, river, plants, waters, and bones and teeth of animals. Sea water contains chlorides, bromides, and iodides of sodium, potassium, magnesium, and calcium, but it is mainly sodium chloride solution. The deposits of dried seas contains these compounds, example sodium chloride and carnallite. Certain forms of marine life contain iodine in their system. Various seaweeds, for example, contain of 0.5% of iodine and child saltpeter contains up to 0.2% of sodium iodate. There are some basic traits as well. Electronic configuration. Their electronic configuration is ns2np5 and there are 7 electrons in their outermost shell. Atomic and ionic radii. The halogens have the smallest atomic and ionic radii in their respective periods due to the maximum effective nuclear charge. The atomic radius of fluorine, like the other elements of the second period, is extremely small. Atomic and ionic increases from fluorine to iodine due to the increasing number of quantum shells. Ionization enthalpy. They have little tendency to lose electron, thus they have a very high ionization enthalpy due to the increase in atomic size. Ionization enthalpy decreases down the group. Electron gain enthalpy. Halogens have maximum negative electron gain enthalpy in these corresponding periods. This is due to the fact that the atoms of these elements have only one electron less than stable noble gas configuration. Electron gain enthalpy of the elements of the group becomes less negative down the group. However, the negative electron gain enthalpy of fluorine is less than of the chlorine. It is due to the small size of fluorine atom. As a result, there are strong inter-electronic repulsion in relatively small 2p of fluorine and thus incoming electron does not experience much attraction. Physical properties. Halogens display smooth variables in the physical properties. Fluorine and chlorine are gases. Bromine is a liquid and iodine is a solid. Their melting and boiling point steadily increase with atomic number. All halogens are colored. This is due to the absorption of radiation is visible resin, which result in the excitation of the outer electron to the higher energy level. By absorbing different quanta of radiation, they display different colors. For example, F2 has yellow, Cl2 has greenish yellow, and Br2 red, and I2 violet color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water, but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons to give colored solutions. One curious anomaly we noticed from table 7.8 in the smaller enthalpy of dissociation of F2 compared of that Cl2, whereas XX bond dissociation enthalpy from chlorine onward show the expected. Chemical properties. The higher oxidation state of the chlorine, bromine, and iodine are released mainly when the halogens are in combination with the small and highly electronegativity fluorine and oxygen atoms. Example, in interhalogens, oxide and oxoacid, the oxidation state of +4 and +6 in the oxides and oxoacids of chlorine and bromine. The fluorine atom has no d orbitals in its valence shell and therefore cannot expand their octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with metals and non-metals to form halides. The reactivity of halogens decreases down the group. The radial acceptance of the electron is the reason for the strong oxidizing nature of halogens. F2 is the strongest oxidizing halogen and it oxidizes other halogen ions in soluble or even in the solid phase. The decreasing oxidizing ability of the halogen in aqueous solution down the group is evident from their standard electrode potential, which are dependent on the perimeters. Analogous behavior of fluorine. Like other atoms of p block present in the second period of the periodic table, fluorine is an anomalous in many properties. For example, ionization enthalpy, electronegativity, or electrode potentials are all higher of fluorine than expected from the trend set by other halogens. Also, ionic and covalent radii, melting point and boiling point enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to the small size, highest electronegativity, and low FF bond dissociation enthalpy and non-availability of the d orbitals in the valence shell. Chlorine are discovered in 1774 by Sill by the action of HCl or MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on the account of its color, Greek, chlorus greenish yellow. Preparation. It can be prepared by many methods, by heating manganese dioxide with a concentrated hydrochloric acid or by the action of HCl on potassium permanganate. Manufacture of fluorine. Dacon's process, electrolytic process. Properties. It is greenish yellow gas with a pungent and suffocating odor. It is about 2 to 5 times heavier than air. It can be liquefied easily into greenish yellow, which boils at 293 Kelvin. It is soluble in water. Chlorine reacts with a number of metals and non-metals to form chlorides. It has an affinity for hydrogen. It reacts with compound containing hydrogen to form HCl. With the excess ammonia, chlorine gives nitrogen and ammonia chloride, whereas the excess chlorine nitrogen trichloride is formed. Interhalogen compounds. When two different halogens react with each other, interhalogen compounds are formed. They can assign general compositions as XS, XX3 and XX5, XX7, where X is an halogen of larger size and X is the smaller size, and X is more electropositive than X. As the ratio between the radii of X and X increases, the number of atoms per also increases. Thus, iodine fluoride should have maximum number of atoms, as the ratio of the radii between I and F should be maximum. That is why the formula is IF7. Group 18 elements. Group 18 consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. All these elements are gases and chemically unreactive. They form a very few compounds because these are considered as noble gas because they have a stable electronic configuration. Occurrence. All the noble gases except radon occur in the atmosphere. Their atmospheric abundance is 1% by volume, of which argon is the major constituent. Helium and subtypes neons are found in minerals of radioactive origin. Example: pitchblende, monazite, elevate. The main commercial source of helium is natural gas. Xenon and radon are the rarest elements of this group. The important atomic and physical properties of group 18 elements are shown in the table 7.12. The trend in some atomic, physical, and chemical properties are discussed as well. Electronic configuration. Its electronic configuration is 1s2, ns2, and p6 except helium, which has 1s2. Many of the properties of the noble gas include their inactive nature and ascribed to their closed cell structure. Ionization enthalpy. Due to the stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radii. Atomic radii increases with the group as we move down and with increase in atomic number. Electron gain enthalpy. Since noble gas have the stable electronic configuration, they have no tendency to accept the electron, and therefore we have the largest positive values of electron gain enthalpy. Physical properties. All the noble gases are monoatomic. They are colorless, odorless, and tasteless. They are sparsely soluble in water. They have a very low melting point and boiling point. Because of the only type of interatomic interaction in these elements is weak dispersion forces. Helium has the lowest boiling point of any known substance. It has an unusual properties of diffusing through, most commonly used as laboratory materials such as rubber, plastics. Chemical properties. In general, noble gases are less reactive. They are inert. Less to chemical reactivity is attributed to the following reason. The noble gas accept heliums have completely filled ns2 np6 electronic configuration in their valence shell. They have high ionization enthalpy and more electropositive electron gain enthalpy. The reactivity of the noble gases have been invested occasionally ever since their discovery, but all the attempts to force them to react to form the compounds were unsuccessful for quite a few years. In March 1962, Neil Bartlett, then a University of British Columbia, observed that the reaction of noble gas. First, he prepared a red compound which is formulated as O2 positive Pt F6 negative. He then realized that the first ionization enthalpy of molecular oxygen was almost identical with the xenon. He made efforts to prepare some types of compounds of xenon and was successful in preparing another red color compound by mixing PTF6 and xenon. After this discovery, a number of xenon compounds are mainly the most electronegativity elements of the group like fluorine and oxygen have been synthesized. The compounds of krypton are fewer, only the difluoride has been studied in detail. Compounds of radon had not been isolated but only identified by the radio tracer technique. No true compounds of argon, neon, and helium are known yet. Thank you.